The core of our galaxy glows like a lantern held inside a storm. Dust coils around it in spirals that look almost deliberate. Gas streams twist, compress, then flare as if something is breathing beneath them. And inside that bright commotion sits a darkness shaped with unnerving precision. A circle so calm that it looks painted rather than formed by collapse. We measure its pull. We trace how stars skid around its edge, and the math insists that space has folded in on itself. But when we stare long enough at the shadow, we sense that the silhouette obeys rules we have assumed rather than rules we have proved. A true black hole contains a singularity, a point where density, mass, curvature, and time reach values no instrument can record. Yet no telescope has ever revealed an infinity. We see only a mask, a region that behaves as though a singularity waits inside, while never offering evidence. Light curves around the boundary, but the curve feels almost too exact. Flares erupt near the edge, then vanish faster than models predict. Even the photon ring, bright and circular, seems to mimic theory with theatrical confidence. Mimicry can be a clue. If an object copies the behavior of a black hole so perfectly that it fools the sky, then perhaps the performance is hiding a different engine. Picture drifting toward the galactic center, a probe tumbling through charged dust and fractured light. The gravitational pull tightens your path. The glow of the accretion region sharpens into a spinning handle of fire. You cross a zone where time itself seems to hesitate, where orbits distort and every beam of light bends sideways. Ahead, the shadow hovers in space like a lid placed over a question. But as you close the distance, something subtle nags at the instruments. The horizon does not swallow light the way a textbook predicts. A faint delay emerges, a hesitation before the darkness claims each photon. The numbers whisper that the surface might not be infinite at all. In astrophysics, we often treat infinities as if they were real objects. But in every other branch of physics, an infinity is a warning that the calculation has broken. When an equation outputs an impossible number, we rewrite the equation. And yet for decades we have accepted that black holes end in a place where mathematics loses meaning. That acceptance should unsettle us. A universe that works everywhere else should not need a region where logic collapses. If gravity leads to a singularity, then gravity itself must be incomplete. Some theorists propose that collapse does not continue forever. Instead, under the extreme pressure inside a dying star, space-time undergoes a transition. The interior does not shrink to a point. It expands into a bubble of dark energy, a region where pressure becomes negative, pushing outward while gravity pushes inward. The two forces balance in a truce that arrests collapse without erasing momentum. The object that forms would look almost identical to a black hole from afar, yet inside it would be a void filled not with destruction, but with a kind of inverted expansion. This object has been given a name: a gravastar, a gravitational vacuum star. If such a thing exists, it would not be gentle. Gravity near its surface would be as fierce as in any black hole. Matter spiraling toward it would heat to millions of degrees. The environment would still be lethal, the physics still razor sharp, but the core would not be a singularity. It would be a chamber where the fabric of the vacuum inflates rather than collapses. Negative pressure creates a counterforce that keeps the object stable. A thin quantum shell, perhaps only centimeters thick, provides the boundary that imitates a horizon. Not a perfect imitation, but close enough that at our current resolution, the two objects cannot be told apart. Imagine approaching that shell. A probe would sense the tidal pull, the curvature, the warping of time, but instead of finding a point of no return, it might encounter a boundary that resists entry in a different way. Light striking the shell could linger longer than expected. Vibrations in the shell might echo through space-time as faint signatures. If a gravastar formed in the aftermath of a stellar collapse, its surface could ring like a drum struck by gravity itself. We have detected gravitational waves from merging compact objects, and the ringdown phase of some events has shown hints, still disputed, of extra structure. Echoes have been reported in some analyses. Faint repeats following the main wave as though the remnant possessed something more than a horizon. These are not confirmations, but they trouble the silence that black holes are supposed to maintain. Our telescopes deepen the mystery. Observations of dark central shadows framed by glowing rings show the shape we expect from a horizon, but these images do not confirm what lies inside. They only show a region where light paths twist so strongly that they form a fog of incomplete information. A perfect event horizon allows no reflection, no surface ripples, no returning light. A Gravastar shell, by contrast, could produce subtle differences in brightness, timing, or polarization. Yet our current instruments cannot resolve the distinction. We stand at a threshold where nature offers two explanations and gives us just enough data to stay uncertain. Why does this matter? Because if gravastars exist, the universe contains a kind of object that stabilizes collapse rather than extinguishing meaning. Instead of ending in a singularity, a star could crystallize into a structure that preserves information on its shell, storing the history of what fell into it. A black hole consumes the past. A gravastar might archive it. If such objects populate galaxies, they may shape their evolution in ways we have not modeled. Their presence would shift how matter accretes, how galaxies grow, how energy circulates at cosmic scales. Think of what that implies for our understanding of time. In a black hole, time appears to end. All paths converge to a point with no future direction. In a gravastar, time continues inside the bubble, expanding outward from a core that refuses to compress further. A star's death becomes a transformation rather than a deletion. The universe might avoid true endings not through mercy, but through mechanism. If collapse typically stops before reaching infinity, then the cosmos may harbor many structures that we misclassify as destructive when they are in fact transitional. Human curiosity thrives on such ambiguities. We have spent centuries refining equations, building instruments, and constructing models that draw the universe into explanation. But occasionally we meet an object that looks familiar, yet behaves like an imposter. The shadows at the centers of galaxies are precisely such objects. They obey our predictions too smoothly, too precisely, as though performing a script. When nature performs too cleanly, we must look for the machinery backstage. A gravastar, if real, is that machinery. It is a star that collapsed almost completely, then paused on the edge of oblivion. A quantum shell holds the line. Dark energy within expands slightly, pressing outward to meet the crushing weight of gravity. The two forces lock together, forming an equilibrium that mimics a black hole without becoming one. From the outside, the facade is flawless. From the inside, the physics tells a different story. Why should the universe bother to construct such objects? One answer is that it avoids infinities, because infinities halt the story. A singularity destroys any prospect of predicting what comes next. A gravastar leaves space-time intact enough to have a future. The universe may prefer continuity over collapse, structure over breakdown. If that preference shows up in the hearts of dying stars, it might also appear in deeper layers of cosmic architecture. The difference between a universe filled with black holes and a universe filled with gravastars is the difference between finality and possibility. This brings us to the paradox that begins our journey. Every observation we have fits the black hole model. Every philosophical discomfort we have points toward an alternative. The line between shadow and shell is thin. Our data is precise yet incomplete, and the universe will not clarify the matter until we improve our reach. We must traverse the space between mimicry and truth, between collapse and refusal. Only then will we learn whether the dark hearts of galaxies are endings or transitions. Let us step deeper into that uncertainty. If the darkness at the galactic core hides a new type of object, then we have misread the universe for generations. And if that object exists, it will reshape our understanding of death, memory, and the architecture of space-time itself. The shadows have waited long enough. If this cosmic mystery pulls you in, Tap like and subscribe to the Quiet Universe channel. The first clue arrives not as a discovery, but as a discomfort. We point our instruments toward the galactic center, expecting the equations of black holes to match each twitch and shimmer of light. They do, almost too perfectly. Every arc of gas, every precession of orbiting stars, every fold of radiation seems to confirm the dominant idea that a singularity hides inside the shadow. Yet the fit is so neat, so absolute, that it feels rehearsed. Nature is often messy. Perfect obedience is unusual. And when the sky behaves with unnatural tidiness, something else may be shaping the script. We have lived for decades with the image of a black hole as the inevitable outcome of collapse, an object so dense that it creates a prison of geometry where no path leads outward. Its horizon is treated as a final boundary. Its core is expected to be a point where the rules of physics admit defeat. We accept this because the idea is mathematically clean. But mathematical clarity is not proof of physical truth. A machine that breaks its own rules is not a machine at all. If a singularity lies at the heart of a black hole, then space-time has a place where it ceases to exist. That should bother us more than it does. The rival in the dark emerges from this unease. It is not a creature imagined to frighten, but an object proposed to mend a contradiction. A gravastar, a gravitational vacuum star, replaces the singularity with a bubble of dark energy. It offers a way for collapse to halt before reaching infinity. Instead of crushing matter into a point, the interior transitions into a vacuum state with negative pressure. This is not a gentle force. Negative pressure pushes outward, countering the irresistible inward drag of gravity. Between the two lies a balance that can stabilize an object more compact than a neutron star but free of any true horizon. From far away, a gravastar behaves like a black hole. It bends light into a glowing ring. It drags space-time until orbits warp and time slows. It swallows matter with ferocity. The imitation is deliberate, not in intention, but in physics. At astrophysical distances, the metrics of a black hole and a gravastar differ too little to detect. This is the heart of the mystery. Two radically different interiors give rise to shadows that appear the same. A single visual anchor captures this paradox. Picture a star on the verge of death. Its core collapses. The density climbs. Photons struggle to escape. Space folds. A black hole would continue that journey unchecked, shrinking the volume until a point forms where curvature becomes infinite. But a gravastar interrupts the collapse. The pressure flips sign. The interior resists further compression. A thin shell forms where quantum matter locks the structure into place. This shell becomes a surface that imitates a horizon with astonishing accuracy. And yet it is not a horizon, not a point of no return, but a membrane that holds the collapse at bay. Understanding this difference matters because it draws a line between destruction and transformation. If black holes are final, the universe contains countless regions where meaning is erased. If gravastars exist, then many such regions store rather than obliterate their past. The two objects shape galaxies differently. Their influence on surrounding matter, their growth, their merger patterns, even their radiation signatures would diverge subtly. The sky offers hints of these subtleties, but our tools are not yet sharp enough to resolve them with confidence. Consider the gravitational waves that ripple through spacetime after massive objects collide. A perfect black hole settles into silence after a predictable ringdown. The tones decay with no extra structure, but a gravastar has a surface. However thin, any vibration of this surface can imprint small delays or secondary pulses onto the wave. Some analyses claim to see faint echoes after a primary merger event, delayed patterns that do not belong in a pure black hole signal. These echoes remain controversial, but controversy itself is a sign of tension in our models. If the data contains more than one interpretation, then the sky might be hinting that our binary categories are not complete. Now turn to the motions of stars near the centers of galaxies. They move as though bound to enormous masses. Their orbits match gravity predicted by compact, dark objects. But this evidence cannot distinguish a horizon from a shell. Stars do not approach close enough to tell us whether they orbit a void or a structure. They only tell us the mass is there and compact. This is a clue with limits. It says something enormous occupies the space. It does not say what the interior looks like. Why would nature produce two such similar objects? The answer may lie in how the universe treats infinities. A black hole invites one. A gravastar avoids one. In classical general relativity, singularities appear naturally, but in quantum theories, infinities are signals of failure. Nature often prevents infinities through new phases, new particles, or new geometric behavior. If quantum gravity forbids true singularities, then gravastars might arise as the real solution while black holes remain excellent approximations at large scales. To see the contradiction more clearly, imagine a bridge overloaded with weight. If the load continues to increase, the bridge will fail. But if the structure adapts, shifting weight across new supports, the collapse can be avoided. A gravastar is that adaptation. It is the universe redistributing pressure into a form that prevents total breakdown. Instead of allowing curvature to explode, space-time rearranges its vacuum state to hold the collapse at a threshold. This raises a question we cannot ignore. What exactly is the rival doing inside the shadow if no singularity forms? The interior expands instead of contracts. The core becomes a place where the vacuum stretches. The shell becomes a surface where fields compress and stabilize. The physics is extreme, but not infinite, and extreme, but finite, is the kind of physics our universe favors. The meaning extends beyond the collapse of stars. If gravastars are possible, then the universe may contain many such objects, not just in galactic centers but among stellar remnants scattered across cosmic time. Primordial gravastars could have formed in the early universe, acting as seeds for galaxies or as candidates for dark matter. Their presence could alter how structures evolve. Their mergers could produce gravitational waves with signatures subtly different from black holes. A universe with gravastars is a universe in which collapse does not erase, but transforms. That transformation carries narrative weight. We think of black holes as the ultimate end, regions that delete history, but a gravastar replaces deletion with storage. Information could remain encoded on its shell, creating a cosmic archive of everything that has fallen in. This idea is speculative, but it aligns with hints from theoretical physics that information cannot vanish. If gravastars preserve information, then the universe may be structured to keep its past, not abandon it. A human-scale image makes this clearer. Think of a collapsing skyscraper frozen in the moment before it hits the ground. All the force is there, all the weight, all the motion. But something absorbs the shock and holds the structure in suspension. A gravastar is that suspended moment turned into an object. Collapse is halted, not reversed, and the energy becomes locked into a new equilibrium. We return now to the rivalry. Black holes dominate our textbooks. Gravastars seem exotic, almost speculative, but the sky does not favor one narrative. It offers data that fits both. The distinction lies outside current reach, hidden behind the limits of resolution and the limits of detectors. The rivalry is not between two monsters fighting for territory. It is between two interpretations of the same shadow, one ending in infinity, the other refusing to allow it. If nature resists infinities, then the rival may be the true heir of collapse. If nature accepts infinities, then black holes reign. Until we refine our instruments, the universe holds the answer behind a mask. To see how this rival saves physics, we have to walk into the singularity's shadow. The collapse of a massive star is supposed to be a simple story. Pressure fails. Gravity takes command. And the core contracts until nothing can halt the descent. Density climbs. Photons scatter and then fail to escape. Neutrons pack tighter than atomic nuclei. In the classical picture, the contraction continues with no boundary, shrinking the volume toward a mathematical point where curvature becomes unbounded. This point is the singularity. a place where laws stop working. We have allowed this idea to stand for decades because it closes a narrative cleanly. But a clean ending is not the same as a real one. If the universe allows infinities, then physics breaks exactly where it is needed most. The contradiction becomes more vivid when we examine the steps that lead toward a singularity. Gravity grows stronger as the radius shrinks. Pressure from particle interactions resists the collapse for a time, but even neutron pressure has a limit. Once the limit is exceeded, the core falls inward. At this stage, the physics of general relativity predicts that nothing remains but the march toward infinite curvature. Yet quantum theory refuses to follow. It does not accept that space-time can be compressed without limit. In quantum models, the vacuum is not empty. It is structured, filled with fluctuations, and these fluctuations influence gravity. When the collapse approaches extreme densities, the vacuum can react, changing the behavior of the core. A new possibility emerges from that tension. Instead of continuing to collapse, the interior can undergo a phase change. This transition creates a bubble of vacuum energy, a region where pressure becomes negative. Negative pressure exerts a repulsive force, not a gentle one, but a powerful tendency to expand. Inside this bubble, the object pushes outward, while gravity pushes inward. Neither force wins. A balance forms at a radius slightly larger than the would-be singularity. The result is a structure with finite density, finite curvature, and a stable interior. This object cannot collapse further. It refuses infinity. Visualize the moment of transition. The core contracts. The density spikes. Instead of forming a point, the vacuum reorganizes itself. A pocket of dark energy appears, filling the interior with a pressure that prevents further compression. A boundary forms between the collapsing matter and the new vacuum. This boundary becomes a shell, thin, rigid, and exotic. It contains the pressure difference and anchors the structure. Outside the shell, the gravitational field looks almost identical to that of a black hole. Inside, the geometry is entirely different. This interior is not a void in the traditional sense. It is a region where space-time expands slightly, a mirror of the universe at large. The expansion is not free. It is held in check by the shell. The interior acts like a small cosmos locked inside the corpse of a star. The bubble maintains its size because any attempt to shrink it increases the outward pressure, and any attempt to expand it increases the inward pull. The equilibrium is delicate but stable. It produces an object where collapse is frozen at the brink, neither continuing nor reversing. Why would the universe prefer such a structure? One reason is that infinities provide no predictive power. A theory that ends with a singularity cannot describe what comes next. A gravastar avoids this failure. By preventing curvature from diverging, it preserves the continuity of the laws. Nature often behaves this way. When a physical quantity approaches a limit that would break the theory, a new state of matter or a new phase transition intervenes. The singularity in a black hole may be the place where our classical model calls for such an intervention. A simple, everyday image captures the essence. Consider a bridge under too much weight. As the load increases, the bridge begins to deform. If nothing changes, it will fail. But if the structure redistributes the weight, shifting the strain across new supports, collapse can be prevented. In a gravastar, the vacuum performs this redistribution. Instead of allowing gravity to concentrate indefinitely, space-time forms new supports in the form of negative pressure. These supports prevent the collapse from reaching an impossible end. The interior geometry offers clues about the nature of time near the core. In a black hole, all paths lead inward. Time becomes aligned with the radial direction. Once past the horizon, movement toward the center is inevitable. But in a gravastar, time does not point toward a singularity. It continues through a region that is smooth and finite. This changes how we understand the fate of matter falling into the object. Instead of vanishing into a point, the matter could become part of the interior environment. The details are uncertain, but the difference is profound. A singularity erases history. A gravastar preserves a place where history can continue. This potential continuity connects to a deeper question. Does the universe truly permit paths that lead to nothing? If a singularity exists, the path of matter and light ends in a place without a future. That is a strange feature for a physical theory. Most laws of nature preserve the ability to predict forward. A singularity is a violation of that principle. A gravastar restores it. By refusing infinity, it keeps the story intact. The shell around the interior is the key to this stability. It must contain the pressure difference between the dark energy core and the external gravitational field. The shell is likely made of exotic matter, a substance with unusual properties. It must be stiff enough to hold the boundary in place, thin enough to allow the object to mimic a horizon, and dense enough to shape the gravitational field. The shell is not a solid barrier in the conventional sense. It is a quantum structure, more like a standing wave than a wall. It forms the interface between two regions of space-time with different behaviors. When light or matter approaches the shell, the interaction is complex. Some paths curve around the object. Others approach the shell and linger before being redirected. The shell may have its own modes of vibration. These vibrations could imprint subtle patterns onto nearby fields. If a gravastar formed from a stellar collapse, the shell would inherit the angular momentum of the original star. This rotation could create additional structure in the boundary. In some models, rotating gravastars can produce effects similar to those of spinning black holes, including frame dragging and energetic jets. The contradiction between the two objects becomes sharper when we consider the information carried by the collapsing matter. A black hole hides information behind the horizon and appears to erase it at the singularity. This leads to the information paradox, a conflict between quantum mechanics and general relativity. A gravastar offers a different path. If the interior is finite and connected, and if the shell can encode information, then the history of what fell in might be preserved. This does not solve every problem. It merely shifts the location where information resides. But it removes the singularity as a threat to the integrity of the laws. One may ask whether this interior is accessible. The answer is likely no. The shell defines a region of extreme curvature. Light cannot easily cross it. Matter falling toward it would experience intense compression. Even if the interior is finite, it remains separated from the outside world by a boundary that behaves almost like a horizon. The difference is that the boundary is not absolute. It is a surface, not a mathematical point of no return. A human scale analogy clarifies the separation. Imagine a sealed vault with walls so thick that sound cannot escape. Inside the vault, events continue, but to anyone outside, the vault remains silent. The shell of a gravastar is such a vault, except that the silence comes from the geometry, not from material walls. The inside is real, but the outside sees only the shadow. Even if we cannot reach the interior, its existence would still alter our understanding of cosmic evolution. Gravastars could compete with black holes in forming at the ends of massive stars. They could merge with one another, producing gravitational waves with slightly different signatures. They could act as seeds for galaxies. They could influence how matter flows in the early universe. Each of these possibilities depends on how often gravastars form, and that is not yet known. The absence of a singularity also changes the nature of time near the core. Instead of ending in a point, time continues through the interior in a direction that is not aligned with collapse. This subtlety has implications for theoretical models that treat the universe as a whole. If the cosmos prohibits singularities, then the Big Bang might have been a transition rather than an origin. Gravastars provide a smaller-scale example of how such transitions behave. We return to the heart of the chapter. The object refuses infinity. It stabilizes collapse at the threshold. It replaces the singularity with a region that remains part of space-time. It transforms the end of a star into a new type of interior. It preserves continuity, where general relativity predicts a break. The rival in the dark is not simply another compact object. It is an argument that the universe favors finite structures over impossible ones. If nature avoids infinities, then what exactly forms at the core of a dying star? The interior of a gravastar is not empty. It is not a hollow cavity waiting to collapse. It is a region pressurized by the strangest substance we know, a form of vacuum energy that behaves as if the universe has inverted one of its deepest instincts. In ordinary matter, pressure pushes outward when compressed. In dark energy, pressure becomes negative. It pushes outward even as space tries to squeeze it. This reversal is more than a curiosity. It is the engine that halts collapse. It is the heart that refuses to be crushed. A pocket of space-time that expands even as gravity demands contraction. To understand what it means to cage dark energy inside a gravastar, we must imagine how the interior forms. Collapse begins as usual. The star exhausts its fuel. The core contracts. Temperature rises. The density climbs to extremes. But when conditions reach a critical threshold, the vacuum reorganizes. Quantum fields shift, and the interior becomes dominated by vacuum energy. This energy acts like a pressure reservoir. Instead of folding inward, it expands gently. The expansion does not tear the object apart. It is contained by the shell, which forms as the boundary between the dark energy bubble and the outer layers of collapsing matter. This bubble behaves like a small universe. It has an equation of state dominated by negative pressure. It influences the curvature inside. It stretches space-time in a controlled way. The interior is not chaotic. It is smooth. It is finite. It is quiet. And yet it is powerful enough to challenge gravity at its strongest. The dark energy core pushes outward with the same determination that gravity uses to crush inward. The equilibrium emerges not by accident, but as a consequence of two immense forces meeting in balance. A human image helps. Imagine a pressure cooker on a stove. Heat builds. Pressure rises inside the sealed pot until the structure holds steady. The cooker does not burst because the design distributes force across its walls. Now turn the picture inside out. The gravastar core is the pressure, and the shell is the pot. But the pressure is negative. It drives expansion, not compression. The shell holds the boundary steady. The analogy is simple, but the physics is not. Negative pressure is a strange and counterintuitive concept. It pulls inward while pushing outward. It stretches space while resisting collapse. The bubble cannot exist without the shell. The shell is the cage. It must be strong enough to contain the vacuum energy, flexible enough to adjust to vibrations, and thin enough to mimic a horizon. It is made of exotic matter, a substance allowed in theory but not found in ordinary stars. Exotic matter can have properties such as negative energy density or unusual stiffness. These properties are required to stabilize the boundary between the two regions of spacetime. Without the shell, the bubble would expand uncontrollably or collapse under gravity. The shell is thin, perhaps no thicker than a few centimeters for an object the mass of a star, yet it bears the entire load of the structure. It is the surface where infalling matter meets resistance. It is the region where light hesitates before reflecting or deflecting. It may vibrate. It may store information. It may behave like a quantum membrane with its own internal modes. The shell is the reason the gravastar mimics a black hole so convincingly. It creates a surface that is nearly but not exactly a horizon. Light can skim it. Matter can approach it, but neither encounters a point of no return. The boundary is real, not mathematical. A clue to the nature of the shell can be found in how it influences gravitational waves. When two compact objects merge, the remnant rings. If the remnant has a horizon, the ringing fades smoothly. If it has a surface, the ringing may contain echoes. These echoes would be signals bouncing between the exterior and the shell. They would be faint. They would be subtle. They would require incredibly precise detectors. Some analyses have claimed to detect such features. Others argue the patterns are noise. But even the possibility that a surface exists suggests that the interior is held in place by a physical structure. A horizon does not vibrate. A shell can. Dark energy itself remains mysterious. It accelerates the expansion of the universe. It shapes the growth of cosmic structure. It dominates the energy budget of the cosmos. Yet we do not know what it is. We only know how it behaves on large scales. Inside a gravastar, dark energy would appear on small scales. It would create a microcosm of cosmic expansion. It would push outward against the shell. It would give the gravastar a heartbeat, not in the biological sense, but in the sense that equilibrium would be maintained through continuous tension. To see why this matters, consider how black holes treat information. In the classical picture, information that crosses a horizon is lost to the singularity. This loss violates quantum principles. The gravastar provides a different structure. Information does not fall into a singularity. It falls toward the shell. The shell may absorb or encode it. The interior is smooth and finite, so information is not erased. It becomes part of the geometry. If this is true, then gravastars do not violate the rules of quantum mechanics. They preserve information in ways that black holes cannot. The difference between an interior filled with vacuum energy and a singularity is not small. It affects the interpretation of the laws of nature. It affects how we think about the death of stars. It affects how we imagine the evolution of galaxies. It affects the fate of matter in extreme environments. A singularity is an endpoint. A dark energy core is a transition. It transforms collapse into stasis. It keeps time flowing. It prevents the universe from reaching a place where prediction ends. One might ask whether this interior could ever be probed. The answer is almost certainly no. The shell is an extreme environment. Pressures are immense. Curvature is intense. Even if we could approach the object, the shell would remain opaque. Yet the physics of the interior still leaves traces in the behavior of the object. These traces might be observable. They might reveal the presence of a core that expands rather than collapses. They might separate the gravastar from the black hole. The meaning of caging dark energy reaches beyond compact objects. It touches on the question of whether vacuum energy can form stable structures. It suggests that the vacuum is not passive. It can respond to pressure. It can stabilize collapse. It can shape matter under extreme conditions. If the vacuum can do this inside a star, it might do similar things on larger scales. It might influence the early universe. It might affect the formation of galaxies. It might create other structures we do not yet recognize. The idea also hints at a deeper symmetry. The universe expands on large scales. The interior of the gravastar expands on small scales. The shell contains both. It separates expansion from collapse. It allows both behaviors to coexist. The gravastar becomes a bridge between two regimes of physics, the cosmological and the stellar. It shows that the same forces shaping the growth of the universe might also shape the fate of stars. We return again to the cage. The shell is the key. Without it, the dark energy bubble would not remain stable. With it, the interior becomes a new kind of space. A space where collapse refuses to complete. A space where the vacuum resists gravity. A space where time continues. The gravastar is not a whole. It is an interior held in tension. It is an argument against the idea that nature allows infinities. It is a structure sustained by balance rather than by breakdown. The shell may be thin. It may be fragile in appearance, but it confines a force powerful enough to counter gravity itself. That contrast gives the gravastar its character. It is delicate in appearance but immense in consequence. It shows that the universe may be more subtle than our simplest models. It suggests that collapse does not always lead to an end. It implies that the vacuum plays a more active role in shaping cosmic objects than we have assumed. Dark energy caged inside a gravastar turns the death of a star into a new beginning. Instead of vanishing into a point, the core becomes a bubble of expanding space-time. Instead of collapsing further, the structure finds equilibrium. Instead of erasing information, it may preserve it. This transformation changes the narrative. A star does not simply die. It becomes a container for a different expression of the vacuum. But a heart of dark energy is useless without something to contain it, and that takes us to the shell. The shell of a gravastar is not an accessory. It is the defining feature, the surface where the entire identity of the object is forged. If the dark energy core is its heart, the shell is its skin, the interface where collapse is halted, and the illusion of a black hole is perfected. To understand the shadow cast by the gravastar, we must first understand the shell, because the shadow is not produced by a horizon, it is produced by a membrane, thin, dense, and quantum in nature. The shell forms when the collapsing star reaches the threshold at which the interior transitions into vacuum energy. At that moment, the pressure flips sign. The new interior pushes outward, the outer layers collapse inward, and the boundary between them becomes a battleground of forces. This boundary condenses into a layer of exotic matter. Exotic matter is not magic. It is a form of matter allowed by the equations of relativity, capable of unusual behaviors that ordinary matter cannot achieve. In the gravastar shell, exotic matter must support negative pressure, maintain structural stiffness, and remain stable under enormous curvature. The formation of this shell is rapid. Once the interior transitions, the pressure imbalance forces the boundary to solidify. The shell then becomes the single structure responsible for holding the object together. It contains the dark energy bubble. It resists further collapse. It shapes the gravitational field around the object. It creates a surface that can vibrate, reflect, and carry information. It is thin, perhaps centimeters across, yet it behaves as though it were the strongest material in the universe. The shell is not smooth in the classical sense. It is a quantum membrane. Its density, tension, and behavior arise from quantum fields that lock into place. These fields give the shell an unusual property. Light that approaches the shell does not behave as it would near a horizon. Instead of being drawn across a point of no return, light interacts with a surface. Some of it curves around, forming the bright ring we observe. Some of it briefly lingers at the shell before being redirected. Some of it escapes at unusual angles. This interaction makes the gravastar look indistinguishable from a black hole at a distance, but up close, the physics is different. The shadow of a gravastar is not absolute darkness. It is the silhouette created by light paths that orbit near the shell, then escape. The interior is not visible because the shell does not allow light to pass. But the shadow is not a horizon. It is a mask created by geometry. To an observer with limited resolution, the difference is invisible. Only a slight variation in the distribution of brightness around the photon ring would betray the presence of a surface. Current telescopes cannot detect this difference. Their images show the same dark circle, whether the object is a black hole or a gravastar. A visual anchor helps clarify the role of the shell. Imagine a drum stretched tightly over a hollow chamber. When you strike the drum, sound waves travel across the surface, bounce inside the cavity, and return. The drum behaves like a resonant boundary. The gravastar shell is similar. It is not struck by a hand, but by the motion of infalling matter, the collapse of the star that formed it, and the tidal forces of the surrounding gravitational environment. These forces create vibrations. The vibrations ripple through the shell. They may even leak into space-time as faint modulations. These vibrations become significant when compact objects merge. If two gravastars collide, the remnant vibrates before settling. These vibrations imprint patterns onto gravitational waves. If the remnant has a shell, the patterns could include echoes. Echoes occur when waves reflect between the shell and the outer environment. A black hole has no surface, so it cannot create echoes. But a gravastar can. Some research teams claim to have identified such patterns. Others argue the signals are noise. The debate remains unresolved, but the possibility alone elevates the importance of the shell. It may be the only place where the distinction between gravastar and black hole becomes measurable. The shell also stores information. If matter falls into the gravastar, it does not vanish into a singularity. It encounters the shell. What happens next is uncertain. The shell may absorb the information. It may encode it as quantum states. It may distribute it across its surface. This process aligns with the holographic principle, the idea that information about a region of space-time can reside on its boundary. A gravastar shell could act as a literal surface where the history of the object is recorded. If this is true, then the gravastar is not only a rival to the black hole, it is a new way for the universe to store memory. The curvature near the shell also mimics that of a black hole. Space-time is bent strongly. Time slows. Paths of light twist. But the mimicry is not perfect. The difference appears in the final approach. In a black hole, the horizon does not allow light to reflect. In a gravastar, the shell may reflect weakly. The reflection is not obvious. It is so faint that most photons still follow trajectories that create the same shadow. But the presence of even a slight reflection can shift the distribution of light around the photon ring. With improved resolution, the difference may become visible. The shell's structure affects more than light and gravitational waves. It influences the dynamics of matter around the object. Jets emerging from the region near the gravastar may behave differently. Accretion disks may show subtle deviations. The flow of plasma may experience boundary effects not present near a horizon. These effects are small, but real. They may produce differences in timing, brightness, or polarization. Astronomers are beginning to look for such signatures. If they are found, they will become the first direct clues that the shell exists. A human-scale image conveys how the shell maintains stability. Imagine a thin but incredibly strong membrane stretched over a pressurized sphere. The membrane holds back a force that should tear it apart, but because the pressure inside is perfectly balanced by the strength of the membrane, the structure remains intact. The dark energy pushes outward. The shell pushes inward. The two forces cancel each other. The result is a static object that resembles a black hole but is something entirely different. If the shell is the key to the gravastar, then the shadow it produces is the key to our confusion. We have assumed that the shadow of a compact object indicates the presence of a horizon, but shadows are not proof. They are the result of bent light, not of event horizons. A surface can create the same shadow if it bends light in similar ways. The gravastar shell performs this function perfectly. It bends light around itself. It absorbs and reflects in ways that are indistinguishable at present. This brings us to the challenge. Our tools are not yet sensitive enough to see the difference between a horizon and a shell. The shadow looks the same. The photon ring looks the same. The accretion disks look similar. Only the smallest deviations, detectable with more precise instruments, can reveal the truth. Until then, the shell hides in plain sight, disguised by the limits of our perception. Yet the shell is not merely a disguise. It is a physical object with properties that matter. It shapes the interior. It shapes the shadow. It shapes the way the object interacts with the universe. If the gravastar exists, then the shell is one of the most important structures in astrophysics. It is the stage on which the rival plays its role. It is the mask that hides the truth. It is the surface where information resides. The shell also points toward broader implications. If the universe uses exotic matter to stabilize collapse, then similar structures might exist elsewhere. Other shells might form in the early universe. Other bubbles might be caged. Other compact objects might mimic black holes. The shell is not an isolated idea. It is part of a larger pattern in which the vacuum plays an active role in shaping cosmic structures. We end with the recognition that the shell creates the shadow, and the shadow hides the interior. The gravastar is an object defined by a surface that stops collapse, a surface that mimics a horizon, a surface that stores information, and a surface that vibrates in ways that may reveal its identity. If the shell can ring, then those rings should leak into the sky as signals. The universe speaks in vibrations. Stars tremble. Gas swirls. gravity stretches space, and the resulting motions carry information across unimaginable distances. But the signals we receive are rarely clean. They are wrapped in interference, buried under cosmic background, and distorted by the very medium they travel through. To learn anything from them, we must listen not just to the obvious tones, but to the whispers beneath them, the small irregularities that hint at structures we cannot see directly. In the search for gravastars, these whispers matter more than the loudest waves. When two compact objects collide, the final moments of the merger produce a ringing pattern known as the ringdown. A black hole settles into this pattern smoothly. Its tones reflect the behavior of a geometry with a horizon. They are predictable and decay without interruption. A gravastar, by contrast, has a surface. When the merged object forms, the shell vibrates. Some of the energy reflects off the shell. Some escapes. Some is trapped for a moment and released later. The result, if gravastars exist, should be faint echoes, delayed signals arriving after the main ringdown. These echoes would be subtle, but they would break the purity of the black hole signature. Detection is not straightforward. Gravitational wave detectors are incredibly sensitive, yet they are also vulnerable to noise, thermal fluctuations, quantum limits, environmental vibrations, and numerical artifacts all complicate the data. Echoes, if present, would be tiny. They would hide in the turbulent murmur of space-time. Some analyses have reported structures that might be echoes. The patterns are controversial. They could be noise, they could be mismodeling, but they could also be the first glimpses of a surface where none should exist. A visual anchor helps. Imagine tuning a radio in an old car late at night, searching for a station with minimal static. The signal comes through clearly for a moment, then crackles, then clears again, hidden in the noise. Faint voices fight for clarity. Sometimes the static conceals them, sometimes it reveals them. The gravitational wave sky is like that. The main event is loud. The ringdown is strong, but the faint echoes, if they exist, linger near the threshold of perception, waiting for instruments sensitive enough to isolate them. The possibility of echoes is tied directly to the physics of the shell. In a black hole, the horizon absorbs everything. There is no reflection. But a gravastar shell is a surface. Energy striking it can rebound. The reflections may be weak, but they are not forbidden. In a merger, the first gravitational waves rush outward. The shell then vibrates. Secondary waves bounce between the shell and the curvature outside. When they find a path to escape, they add small pulses to the overall signal. These pulses are the echoes. They would be spaced by the time it takes for waves to travel between the shell and the exterior spacetime, creating a repeating pattern that slowly fades. The structure of the echoes depends on the thickness, density, and composition of the shell. A thicker shell would produce softer rebounds. A thinner shell might create sharper reflections. The rotation of the gravastar would add further complexity. Rapid spin could stretch the shell, altering the timing between pulses. The curvature outside the object also shapes the path of the waves. The echoes would not be perfect copies of the main signal. They would be distorted, stretched, and shifted. The signature would be messy, but even a messy signature can be meaningful. We must also consider electromagnetic clues. Light near a gravastar behaves almost the same as near a black hole, but the shell may subtly influence the brightness of the photon ring. If the shell reflects even a small amount of radiation, the inner edge of the accretion structure might show a slightly different profile. The difference would be small. Current telescopes cannot detect it, but future arrays with higher resolution might see small deviations, perhaps fluctuations in brightness or polarization that indicate the presence of a surface. Why do these small signals matter? Because they are the only accessible fingerprints of the gravastar. We cannot see the interior. We cannot touch the shell. We can only observe how the object interacts with its environment. If the shell vibrates, the vibrations must leave traces. If the shell reflects energy, the reflections must leave patterns. If the interior is filled with vacuum energy, the boundary must respond to forces in ways a horizon cannot. Every deviation, no matter how faint, is a clue. A human-scale image reveals the challenge. Picture sitting in a crowded room where everyone is speaking at once. In the middle of the noise, someone whispers your name. To hear it, you must filter out every other sound. You must listen for something that does not fit the general murmur. Finding Gravastar signals is similar. We are trying to detect a whisper beneath the roar of cosmic events. The whisper may be there, it may not, but the attempt to isolate it forces us to sharpen our tools. Beyond gravitational waves and light, another set of clues may come from timing irregularities. Pulsars orbiting near compact objects send regular signals. If a Gravastar shell exerts different forces than a horizon, the pulsar timings might drift in unexpected ways. The effect would be tiny, but measurable with future instruments. The drift could reveal something about the surface tension of the shell or the behavior of the interior. Pulsars have already been used to test gravity near massive objects. Using them to distinguish between a horizon and a membrane is a natural next step. The search for Gravastar signals also connects to the broader problem of noise itself. Noise is not simply the absence of information. It is a mixture of signals we cannot yet decode. The early universe was once noise. Cosmological background radiation was once noise. The discovery of gravitational waves transformed what was once theoretical noise into a new observational frontier. The boundaries of knowledge advance when noise becomes signal. Gravastars, if real, may be hiding in the next layer of noise. The possibility that some black hole candidates might be gravastars raises another question. How many, if even a small fraction of compact objects are gravastars? Their combined influence could shape galactic structures. They would merge differently. They would interact with matter differently. They would emit different gravitational signatures. Their presence would leave an imprint on the distribution of mass across cosmic time. Detecting even a handful would reshape our understanding of collapse, formation, and evolution in the universe. There is another layer to the mystery. The absence of direct confirmation does not weaken the idea. It strengthens the challenge. A true scientific frontier is rarely visible in clear contrast. It appears in contradictions, in tensions between data and theory. Gravastars lie in that space. They are consistent with known physics. They solve problems that black holes create. They mimic black holes so perfectly that only faint signals can betray them. Their existence would be transformative. Their absence would refine our models of collapse. Either outcome advances knowledge. The search continues in laboratories as well. Simulations attempt to model how a shell would behave under extreme curvature. The results suggest that the shell could support oscillation modes unique to gravastars. These modes might couple weakly to gravitational waves. If so, they could leave imprints that are not echoes but distortions of the main ringdown. These distortions would be even harder to detect. They would require detectors with sensitivity far beyond current capabilities. But progress continues. Each improvement in precision brings us closer to distinguishing between horizon and shell. At the heart of this chapter is the idea that signals can reveal what shadows hide. The Gravastar competes with the black hole by producing nearly identical gravitational and electromagnetic behavior. The differences are small, but they exist. They hide in the way waves bounce. They hide in the way light curves. They hide in the statistical variations of brightness. They hide in the timing of distant pulsars. They hide in the low-level noise of detectors built to measure space-time itself. The path forward is clear. We must refine our ability to separate signal from noise. We must search for repeated patterns in gravitational wave data. We must compare theoretical models of echoes with observations. We must examine the brightness and polarization of photon rings with higher resolution. We must use pulsars as probes of strong gravity. We must treat noise not as a nuisance, but as the medium through which gravastars reveal themselves. If the noise hides a pattern, we must ask where these objects actually come from. A massive star does not choose a single ending. Its death is a forked path with branches shaped by mass, pressure, rotation, and the physics of its collapsing core. For most of the universe's history, astronomers believed the fork had only two major outcomes. If the star was modestly massive, it died into a neutron star, a sphere of compressed nuclei where neutrons crowd together in a city-sized structure. If the star was heavier, collapse continued past the neutron limit and formed a black hole, a region where gravity overcame every resisting force. This two-branch map was simple. It was elegant. It seemed complete. But the universe rarely confines itself to the simplest story, and the deeper we study collapse, the more obvious it becomes that the map is incomplete. The forked death begins with the supernova. The star, exhausted of fuel, can no longer support its mass. The core contracts. Outer layers crash inward with violent acceleration, then rebound, blasting material into space. The core remains behind, compressed into a dense object. At this boundary, the history of each star diverges. Under certain pressures, the core stabilizes into a neutron star. Under more extreme pressures, it pushes beyond that stability. But what happens in the narrow region between those outcomes? The universe does not necessarily jump from one state to the next without intermediate forms. Rather, it explores every possible configuration allowed by physics. Gravastars may be one such configuration. To understand the fork, consider what determines the fate of the core. One factor is the equation of state, the relationship between pressure and density in nuclear matter. For neutron stars, the equation of state is stiff. As the star contracts, pressure increases dramatically, providing support against further collapse. But this pressure has limits. When mass exceeds a certain value, no stiffness can maintain stability. Gravity overwhelms the nuclear forces, and the core moves toward black hole formation. Yet the exact mass that marks this boundary is uncertain. It depends on the composition of the core, the temperature, the rotation, and the presence of exotic particles. It is entirely possible that some cores reach this threshold but find a new equilibrium before collapsing completely. This is where the gravastar becomes relevant. If dark energy forms inside the collapsing core, negative pressure replaces the neutron pressure that once held the star up. This changes the outcome. Instead of shrinking into a point, the core undergoes a transition. A bubble of vacuum energy appears. The collapse halts. A shell forms. The gravastar emerges as a third branch of the fork. Not a direct competitor to neutron stars or black holes, but a different solution to the problem of collapse. It is the result of a core that reaches extreme conditions and chooses balance over infinity. A visual anchor helps make sense of the fork. Picture driving toward a junction where two roads branch in opposite directions. If you continue straight, you must choose one or the other. But imagine discovering a hidden side road that curves gently between them. This side road is narrow, rarely taken, and easily overlooked. Yet it exists. The gravastar is that side road in the evolution of collapsing stars. It lies between the neutron star branch and the black hole branch. It does not replace the two main outcomes. It adds nuance to them. Another way to see the fork is to examine mass ranges. Stars below a certain mass produce white dwarfs. Above this, they produce neutron stars. Above that, the core becomes too dense to remain stable and collapses further. But this oversimplification hides the complex conditions inside the core. If the dark energy transition occurs at a particular density, gravastars can form from stars whose masses fall in the upper range of neutron star formation or the lower range of black hole formation. The transition provides an escape from singularity. These objects would appear as black hole candidates but lack actual horizons. They would resemble neutron stars in some properties and black holes in others. Their masses might fall in regions where neutron stars should not exist, yet where black holes are not inevitable. The rotational dynamics of the core add further complexity. A rapidly spinning star exerts centrifugal forces that counteract gravity. This can delay collapse or change the profile of the core. High rotation rates create anisotropies, meaning collapse may not proceed uniformly. If a dark energy transition depends on achieving certain thresholds, rotation can influence whether a gravastar forms. Faster rotation could help the shell stabilize. Slower rotation could allow collapse to continue. The fork becomes a network of intertwined pathways rather than a single branch split. There is another factor. Magnetic fields inside collapsing stars can reach extreme intensities. These fields influence the motion of charged particles and the structure of the core. They can funnel matter, change dynamics, and create jets. If the formation of a gravastar depends on how the interior distributes stress, magnetic fields could help or hinder the transition. A strong magnetic field may stiffen regions of the core, allowing the shell to form. A weaker field may fail to provide enough structure. The interplay of rotation, magnetism, and vacuum physics shapes the outcome in ways we do not yet fully understand. This layered complexity raises a crucial question. How many stars follow the hidden path of gravastar formation? If the path requires fine-tuned conditions, gravastars may be rare. If the transition occurs naturally in a wide range of circumstances, they may be common. Their presence among compact objects could be significant. Their mergers could produce unique gravitational wave signatures. Their interactions with matter could subtly alter the behavior of accretion disks. Their stability could influence how galaxies distribute mass. Even rare gravastars could shape the evolution of the cosmos. A human-scale image captures the sensitivity of the fork. Imagine a traffic intersection where a slight turn changes the destination by hundreds of kilometers. The star's collapse is like that. A subtle shift in mass or rotation or pressure determines whether it becomes a neutron star, a black hole, or something else entirely. The gravastar emerges when conditions are balanced on a razor edge, when collapse meets vacuum physics at just the right moment. To test the prevalence of gravastars, astronomers study compact objects at the boundary of neutron star and black hole masses. Stars around 2 to 3 solar masses occupy the zone where transitions can occur. Some objects in this mass range appear too small to be black holes and too large to be neutron stars. They may be gravastars. Their radiation profiles, spin rates, and gravitational influence become important clues. If their behavior deviates from expectations, the deviations might indicate the presence of a shell rather than a horizon. Another observational avenue involves binary systems. When compact objects orbit each other, they exchange mass. This exchange pushes them toward or away from collapse thresholds. A neutron star in a binary may gain mass until it reaches instability. In classical models, it becomes a black hole. In the gravastar scenario, the interior might transition before a horizon forms. The result is a binary containing a gravastar. The gravitational waves from mergers in such systems would differ from pure black hole mergers. The differences would be small, but detectable with future instruments. The forked death also carries consequences for the information paradox. Neutron stars preserve information in their structure. Black holes appear to erase it. Gravastars preserve information on their shells. If gravastars are common, they could reduce or even eliminate the need for information to be lost at horizons. This shifts the role of singularities from inevitable outcomes to avoidable ones. The universe may rarely produce true singularities. Instead, it may prefer stable end states that refuse infinity. There is also the question of cosmic evolution. If gravastars formed early in the universe, their density and stability could influence the growth of galaxies. They could serve as seeds for structures. They could mimic black holes in gravitational behavior, yet behave differently in mergers. Their presence in the early universe could leave imprints on the distribution of matter. These imprints would distort background signals. They might be detectable in subtle variations of cosmic background radiation or gravitational lensing. Despite these possibilities, the fork remains hidden behind observational limits. Our tools cannot yet distinguish between a horizon and a shell. We cannot measure the interior of a compact object. We infer structure from behavior. We map mass, spin, and radiation. We watch how objects distort space-time, but the forked death leaves only faint clues. The universe hides its variety behind shadows that look deceptively alike. The fork also challenges our understanding of stability. Neutron stars are stable because of nuclear pressure. Black holes are stable because nothing escapes their horizons. Gravastars are stable because the vacuum inside pushes outward. Three different mechanisms, three different pathways, three different fates for collapsing matter. The existence of all three would make the universe richer and more complex than the classical model suggests. The forked death is not just a diagram of stellar endings. It is a comment on the nature of collapse itself. Collapse is not simply destruction. It is transformation. It is the universe searching for a configuration that resists infinity. Neutron stars resist with nuclear forces. Gravastars resist with vacuum pressure. Black holes yield, allowing collapse to complete its path. The fork is not about choosing one over the other. It is about recognizing that the universe may take all paths allowed by physics. If forks shape the fates of stars, they must also shape the fate of galaxies. A star that becomes a gravastar alters the gravitational landscape around it differently than a star that becomes a black hole. Its mergers produce different waveforms. Its interactions with matter follow different rules. The forked death influences the cosmic web in ways we are only beginning to imagine. But those forks do not end with stars. They may reshape whole galaxies. A gravastar is not only a rival to the black hole, it is also a machine. Its structure combines intense gravity, a pressurized interior, and a quantum shell capable of storing information. If these objects exist in large numbers, they do more than mimic black holes. They become engines that redistribute energy, guide the formation of galaxies, and preserve the memory of matter that falls toward their boundaries. The universe may have built them not as anomalies, but as tools that shape cosmic structure. To begin, consider how galaxies grow. At the centers of most large galaxies sits a compact object with the mass of millions or billions of suns. Traditionally, we assume these are supermassive black holes. Their gravity organizes stars, drives accretion disks, and powers jets. But if even some of these central objects are gravastars, the engine at a galaxy's core changes character. Instead of a singularity hidden behind a horizon, we have a shell that interacts with infalling matter, absorbs information, and compresses energy at a finite surface. The difference matters. In a black hole, matter crossing the horizon enters a region that does not return signals. The horizon swallows radiation and erases details. A gravastar shell acts differently. It can trap matter, reflect a portion of incoming energy, and store information on its surface. This changes how accretion disks behave. The innermost stable orbit may shift. The rate at which energy is released could differ. Jets emerging from the poles of rotating objects may be influenced by the shell's structure. These differences are subtle, but across cosmic time they could alter how galaxies evolve. A helpful visual anchor can reveal the role of these engines. Imagine a data center whose racks of servers produce so much heat that they help warm entire districts. The servers store information while the heat they generate influences the environment around them. A gravastar is similar. Its shell may encode data while its immense gravity shapes the behavior of stars and gas. It is a library built inside a power plant. The storage and the energy distribution are not separate functions. They are linked. This idea leads to a natural question. What kind of information could a gravastar store if matter falling toward the shell is not destroyed? Its quantum details may be preserved as states on the surface. The shell becomes a vast archive of everything absorbed. These stored states might not be readable from the outside. They may never reveal themselves to observers, but their existence would resolve the problem of information loss. Instead of vanishing at a singularity, information becomes part of the geometry. The concept aligns with the holographic principle. In this view, the amount of information a region can contain scales with its surface, not its volume. A gravastar's shell makes this literal. It is the surface that holds the information. The interior is smooth and finite, not a singular point. This rearrangement allows the universe to obey quantum rules while preserving the strong gravity environment expected near collapsed stars. Yet gravastars do more than store. They also shape. If dark energy fills their interiors, the pressure could influence their long-term behavior. The interior might expand slowly, altering the balance between shell tension and gravitational pull. This interplay may contribute to the stability of the object. It may also affect how the shell responds to vibrations. These vibrations, in turn, influence how the gravastar interacts with its surroundings. Across billions of years, these interactions accumulate. A central gravastar in a galaxy could regulate star formation. It could influence gas flows. It could alter the distribution of angular momentum. This is not speculative fantasy. Black holes already do these things. Jets from supermassive black holes can heat the surrounding gas, suppressing star formation. If gravastars mimic these effects while adding new layers of behavior, they become engines that guide cosmic evolution. What about the early universe? After the Big Bang, the cosmos was a field of dense energy. Fluctuations in density produced the first seeds of structure, under the right conditions. Some regions could collapse into compact objects almost immediately. These primordial objects would be small, dense, and numerous. If gravastars can form in such conditions, they might be part of the dark matter population. Their masses would range from small fractions of a solar mass to thousands of solar masses. Their shells would store information about the earliest epochs. Their gravitational influence would help shape the growth of galaxies. We have not confirmed such objects, but the possibility is consistent with some interpretations of early universe physics. Primordial compact objects have long been considered as candidates for dark matter. If some of these objects are gravastars, their unique structure would add richness to the dark matter story. They would be dark because their shells allow little radiation to escape. They would be massive enough to bend light. They would be stable over cosmic time. They would not evaporate like small black holes. Their existence would reshape our understanding of the universe's hidden mass. A human-scale analogy makes the idea of hidden archives more vivid. Imagine walking through a vast library in darkness. Each shelf holds volumes written in a script you cannot read. You cannot open the books. You cannot shine a light on them, but you sense the presence of stored knowledge. Gravastars may be similar libraries. Their shells hold information that endures. Even if we cannot decipher it, the universe might be filled with such silent archives. Beyond information, gravastars also act as engines of energy. Consider a rotating gravastar. The rotation stretches the shell. This stretching can produce differential effects similar to frame dragging. The shell may exchange angular momentum with the surrounding disk. It may interact with magnetic fields. It may influence how jets form. These effects are hard to distinguish from those produced by rotating black holes. But the presence of a surface could produce slight differences in timing, structure, or polarization. The thinness of the shell is essential. If the shell were thick, it would absorb too much energy. If it were too thin, it would collapse under pressure. Its whole thickness must be tuned by the balance between dark energy inside and gravitational pull outside. This fine balance makes the shell incredibly sensitive to disturbances. Vibrations may persist longer. Certain oscillation modes may be unique. These modes could interact with electromagnetic radiation, altering the patterns we observe. If gravastars act as engines, they may also act as relics. Their shells might preserve information not only about infalling matter, but about the processes that formed them. A gravastar created in the early universe could store a record of high-energy conditions. A gravastar formed from a massive star could preserve the geometry of collapse. These structures would encode details about physics we cannot otherwise access. They would be fossils of cosmic history, preserved not in rock, but in space-time. Another possibility involves clustering. If gravastars formed early, some regions of the universe might contain many of them. Their combined gravitational pull could shape large-scale structures. They could influence the distribution of galaxies. They could alter the growth of clusters. Their shells might interact through subtle gravitational effects. These interactions would be nearly invisible at large distances, but would contribute to the fine texture of the cosmic web. The concept also touches on the question of cosmic acceleration. Dark energy drives the expansion of the universe on large scales. If gravastars contain dark energy inside, they become small pockets of cosmic behavior on stellar scales. The universe might use these objects to distribute vacuum energy in structured ways. This is speculative, but not impossible. If dark energy can be confined, then gravastars could act as reservoirs. Their stability suggests that vacuum energy is not always uniform. It can be organized. The gravastar's role as an archive has implications for entropy. Black holes are often considered the ultimate entropic objects. They maximize disorder. Their entropy scales with surface area. Gravastars, with their shells, may have comparable or even higher entropy. Their ability to store information could make them central to the universe's bookkeeping. Instead of allowing information to vanish, the universe may hide it behind surfaces we cannot penetrate. The presence of gravastars also changes our expectations for cosmic storms. Jets from compact objects can extend thousands of light years. If gravastars power these jets, the energy distribution at their bases might differ. Slight variations in jet structure could reveal the nature of the engine. Jets might flicker differently. They might carry different polarization signatures. They might reveal traces of surface interactions. All of these possibilities paint a picture of gravastars not as exotic anomalies, but as active participants in cosmic architecture. They guide, they shape, they store, they stabilize. They are not simply alternatives to black holes. They are engines with multiple functions. If the universe already runs on such engines, what would a more advanced mind do with them? A gravastar is already a bold proposition, but its implications grow stranger when we consider how an older civilization might interpret such objects. If gravastars exist, they are stable, information-rich, energy-dense, and gravitationally powerful. They could serve as tools, repositories, or laboratories. They could be the natural endpoints of stellar collapse and also the raw material for extraterrestrial engineering. To imagine how another mind might use them is not to drift into fantasy. It is to follow the logic of physics to a place where curiosity meets possibility. Begin with the idea of information. A gravastar's shell could encode quantum states of everything that has fallen toward it. The information is locked behind a barrier we cannot cross. We lack the sensitivity to detect its patterns. But a civilization with more advanced instruments might not share that limitation. If the shell behaves like a quantum surface, its oscillations could reveal faint traces of its stored history. These traces might consist of patterns in polarization, shifts in timing, or resonances in gravitational waves. Another species might have already learned how to read such patterns. For them, gravastars might not be shadows. They might be libraries. A visual anchor helps. Picture a canyon at dusk. A person stands at the edge and shouts. The echoes return from hidden chambers carved by wind and time. The returning sound carries information about spaces the eye cannot see. To us, gravastars are like those canyons. We hear their echoes faintly in gravitational waves. But an advanced observer might shout in frequencies we have not imagined, receiving answers written in the shell. This leads to a provocative thought. If a civilization wants to store vast quantities of information, it needs a stable and long-lasting structure. Computer systems decay. Stars die. Planets change. Gravastars do not share these vulnerabilities. Their shells remain stable for billions or even trillions of years. They are difficult to disrupt. They are shielded from most external influences. They offer surface area that scales with gravitational mass. They are cosmic vaults built by collapse and held intact by vacuum energy. The universe may have constructed them as archives long before life arose. Others may have learned to use them. Another possibility lies in energy. A gravastar's environment is extreme. The gravitational pull near its shell can accelerate particles to high energies. Matter falling toward the boundary releases enormous power. Advanced technology might harness this energy. not in the mythical sense of tapping stars, but in the practical sense of gathering power from accretion flows or exploiting tidal forces near the shell. Such a civilization might build structures in orbit around a gravastar, using its gravity to stabilize habitats or extract resources from nearby plasma flows. Jets emerging from gravastar like engines could also be used. If the shell rotates, it may interact with magnetic fields in ways similar to spinning black holes. These interactions could beam energy outward. A civilization could position receivers in the path of such beams. We already imagine harvesting energy from black holes by spinning them down. Doing something similar with gravastars would be easier because the presence of a surface provides more points of interaction. We must also consider communication. If gravastar shells vibrate, the vibrations can imprint patterns on gravitational waves. These patterns could serve as markers deliberately encoded by an advanced species. The waves would travel across the cosmos without strong attenuation. A species with sufficient precision could broadcast messages by modulating the shell. Such a system would be invisible to us, but obvious to anyone who knows what to search for. It is equally possible that gravastars formed naturally in the early universe might contain signatures of the conditions from which they emerged. Their shells could preserve traces of primordial fields, early fluctuations, or high-energy interactions that we cannot recreate. Another species might treat gravastars as probes of cosmic history, not engines, not repositories, but instruments for studying the universe's earliest phases. A human-scale analogy conveys this more clearly. Imagine walking through a vast observatory built by an ancient culture. The instruments are still running, the data is still stored, but you do not understand the language or the controls. You know the structure has purpose, but not what that purpose is. Gravastars could be such observatories. Their shells might contain encoded histories of the cosmos, placed there by the universe itself or by civilizations capable of shaping space-time. There is also the possibility that advanced species have cataloged gravastars. Perhaps they classify them by shell thickness, vibrational modes, interior pressure, or formation history. They might track those that formed from supernovae separately from primordial gravastars. They might use them as markers for navigation, or as waypoints in deep space. The idea is not fiction. It arises naturally when we ask how beings far older than us would interact with structures defined by vacuum energy and boundary physics. If gravastars can be tools or archives, they could also be signals. A civilization might modify the shell, creating oscillations that relay information across space. These oscillations could be hidden in the noise. To us, they appear as slight irregularities in gravitational wave data, but to those who know the encoding scheme, they are messages written in space-time itself, a whisper carried by the geometry of collapse. Another perspective comes from considering why we have not seen such signs. Our detectors may be too young. Our analyses may be too coarse. We may not know what patterns to search for. If signals are encoded in shell vibrations, they would require extraordinary sensitivity to detect. Even slight errors in calibration could hide them. As our tools improve, we may begin to see structures that do not match any natural processes. These structures could be artificial, or they could be remnants of early cosmic transitions. Either way, the gravastar becomes the medium. The possibility of alien use raises broader questions about the nature of horizons. Horizons limit what we can see. They conceal more than distance. They hide entire regions of spacetime. But if gravastars mimic horizons without being true horizons, then the universe contains surfaces that pretend to hide the interior but actually store everything that touches them. To a species capable of probing these surfaces, a gravastar is not a boundary. It is a portal to knowledge hidden behind curvature. The question extends even further. What if the entire observable universe behaves like a gravastar interior? We see only a limited region. Beyond our horizon lies more spacetime. The cosmos may be a bubble of vacuum energy contained by a larger geometry. If that is true, then we live inside a structure similar to a gravastar. Our horizon is not a boundary of reality. It is a surface defined by expansion and limited by light. We are inside a shell of our own, one that hides information from us, just as a Gravastar shell hides information from outside observers. This comparison is not meant to claim that the universe is a Gravastar. It is meant to reveal the symmetry between the two. Both involve interior expansion. Both involve surfaces that behave like horizons. Both preserve information in ways we do not yet understand. If a Gravastar is a small-scale reflection of cosmic behavior, then studying these objects may reveal how the universe itself operates on the largest scales. We must also acknowledge our limitations. We cannot detect artificial manipulations of Gravastar shells unless they are dramatic. We cannot read encoded information unless the oscillations are strong. We cannot distinguish between natural and artificial signals until our theories improve. But the absence of recognition is not the absence of possibility. The universe does not shape its objects only for our understanding. If Gravastars serve multiple roles, they may be part of technologies we have not yet imagined. Some teams propose that Gravastars could host stable orbits ideal for artificial structures. A ring of satellites placed near the shell could harness energy or collect data. The gravitational environment would be extreme but predictable. The stability of the shell could make such orbits safer than orbits near true horizons. If this is possible, the presence of unexplained structures around compact objects might become a clue. The idea of alien catalogs is not speculation for its own sake. It follows from the recognition that Gravastars are surfaces that encode. If a species seeks to preserve history or manage energy on cosmic scales, these surfaces are natural tools. They outlast stars. They resist disruption. They behave predictably. They hide their contents behind physics rather than behind locks. At the end of this chapter, one thought remains. To us, Gravastars are possibilities concealed in shadows. To a more advanced intelligence, they might be shelves in a cosmic archive or engines in a cosmic machine. Our challenge is not to assume intent, but to expand our imagination far enough to recognize the range of what these objects could be. To know what any of this means, we have to step back and ask what kind of universe builds such things. The long arc of collapse leads us to a quiet frontier, beyond the equations, beyond the models, beyond the rivalry between horizon and shell. Something deeper waits in the dark. The Gravastar is not merely a compact object, it is a meditation on how the universe handles endings. It challenges the expectation that death, whether of a star or a structure, must culminate in a place where meaning falls apart. If the Gravastar is real, then the universe does not end things by crushing them into singular points. Instead, it transforms them, suspending collapse at the edge of impossibility and replacing the final fall with a new interior. The philosophical weight of this idea becomes clear when we reconsider what a singularity represents. A singularity is not a location in space. It is a confession of ignorance, a point where our theories decline to speak. It is the boundary beyond which our understanding cannot pass. If nature avoids singularities, then nature avoids places where knowledge is forbidden. The Gravastar becomes a counter-argument to fatalism, a structure that suggests reality is more coherent than our equations imply. It keeps the interior finite, the future open, and the evolution of space-time intact. This reveals a new perspective on what a shadow is. We have long thought of the shadow at a galaxy's center as a symbol of annihilation. But in the Gravastar scenario, the shadow is not destruction. It is concealment. It is the quiet surface behind which information is preserved. The darkness becomes protective rather than terminal. A shadow that hides an archive is different from a shadow that hides an abyss. The distinction matters not only for physics, but for how we imagine the structure of reality. A visual anchor brings this into focus. Imagine walking along a coastline during twilight. The water is dark but shimmering. Beneath the surface, life continues uninterrupted. The darkness is not emptiness. It is depth. A Gravastar's shadow may be like that. We see only the curtain. We assume the void. But beneath the thin shell lies a region filled with possibilities. A pocket where time still flows, where geometry remains smooth, where collapse has been rerouted into a new kind of stability. This recognition invites us to ask whether the universe contains more such pockets. If stars can become gravastars, could the cosmos itself follow similar principles? The universe began in a state of extreme density. Some ideas suggest that the Big Bang was not a singularity, but a transition, a change in the state of the vacuum. If that is true, then the universe might be a large-scale analog of a gravastar interior, a region of expanding space-time surrounded by boundaries we cannot observe. Our cosmic horizon might be a shell of its own kind, not a hard edge, but a limit defined by expansion. To put it another way, the gravastar is not only a physical hypothesis, it is a reframing of how we understand confinement and openness. It replaces the idea of an endpoint with the idea of a threshold. Instead of a place where physics ends, it gives us a place where physics transforms. This shift affects not only astrophysics, but also the way we think about our position in the cosmos. We live in a universe that has room for transitions, not just terminations. There is also a human parallel in the gravastar's refusal of finality. In our own lives, we tend to search for boundaries that cannot be crossed, for lines where decisions end and stories close. But the gravastar suggests that boundaries can conceal new beginnings. A collapse halted by vacuum pressure is not unlike a moment of crisis that becomes a point of redirection rather than destruction. The metaphor is simple but resonant. Where we expect endings, the universe may place surfaces that hold possibility. Consider the quote, reframed for our context, that a place where equations fail is not the edge of reality but the edge of understanding. The gravastar embodies this. It replaces failure with structure. It replaces the infinite with the finite. It turns a singularity into a conversation between gravity and vacuum, a balance rather than a breakdown. This echoes a broader truth. The most extreme events in the universe may not be catastrophes, but reconfigurations. This idea gains strength when we examine how the gravastar handles time. Inside a singularity, time ends. Inside a gravastar, time continues. The continuity of time is a profound statement about the nature of the universe. If time cannot be destroyed, then the cosmos is more consistent and more elegant than we have believed. It avoids the absurdity of paths that lead nowhere. It preserves causality. It protects the future from collapsing into nothing. The philosophical echo extends further. If gravastars store information, then the universe does not discard its past. It absorbs it. It rearranges it. It keeps it intact behind boundaries we cannot penetrate. This invites a question about memory on cosmic scales. Does the universe preserve everything? Are gravastars nodes of remembrance, structures where the records of collapse are maintained rather than erased? If so, every shadow in the sky becomes a kind of monument, a quiet testament to the history of stars. This also reframes how we view our own search for meaning. The universe, if it avoids singularities, is a place where continuity wins over rupture. We live in a cosmos that does not throw away information lightly. This mirrors our own attempts to preserve culture, knowledge, and experience. The gravastar becomes a model for resilience. It suggests that even where collapse seems irreversible, hidden processes may protect what matters. At its core, this chapter reflects the possibility that the universe does not permit absolute annihilation. It permits transformation. It preserves coherence. It finds ways to redirect collapse into new states of being. The gravastar is a symbol of this philosophy. It stands at the threshold between destruction and endurance. It tells us that the cosmos is structured in ways that resist breakdown. We can also consider the moral dimension of this idea, not in the sense of ethics, but in the sense of cosmic narrative. A universe filled with singularities is a universe where the deepest corners end in silence and erasure. A universe filled with gravastars is a universe where the deepest corners hold memory. One feels barren. The other feels complex, layered, unfinished in a meaningful way. The difference is not trivial. It shapes how we interpret the nature of reality itself. As we pull away from the gravastar and its shadow, the final image becomes clear. A solitary object floats in a quiet region of space. Dust spirals nearby. Light bends around it in a perfect ring, but the darkness at the center is not a void. It is a shell, thin as breath, containing an interior that refuses to collapse into nothing. It is a reminder that even the greatest pressures in the universe can be met with structures capable of preserving coherence. The cosmos holds its secrets in surfaces, not in abysses. And so the question that closes our journey emerges naturally. If collapse never truly ends, and if the universe preserves what falls toward its darkest places, then what does it mean for anything to be finished at all?